This program is brought to you by Stanford University.
Let's do a little bit of mathematics, some simple mathematics. Probably most of you know the mathematics. The mathematics of spheres. Spheres in any number of dimensions are the special geometries which are uniform. And uniform means that they have constant curvature. If you have gone through the previous quarter, you have an idea of what curvature means. If you haven't been through, you can more or less imagine what curvature means, and you can imagine that a sphere is a very uniform surface. The curvature at every point is the same, but let's just discuss spheres a little bit, which are positively curved surfaces, and the cosmology, which is the cosmology of a spherical universe. Incidentally, sphere, when one talks about a spherical universe, one is talking about the geometry of space, not space-time. And then we can talk about is it the opposite? Well, the other possibility, which is the possibility of negative curvature. There is also a space which is uniformly negatively curved, harder to visualize, harder to draw on the blackboard, but I'll try to give you some feel for it. And then the cosmology, which is based on a negatively curved universe. And finally, what I would like to do tonight, well, we may get to more than that, but at least I would like to get to the connection between the equations that we've written down so far for cosmology and the general theory of relativity, Einstein's equations. So let's just start, in order to all be on the same page, with what a sphere is. A d-dimensional sphere. D I use for dimension. Okay, I'll do it by example. A two-sphere. One speaks of a one-sphere, a two-sphere. Well, let's start with a one-sphere. A one-sphere, a two-sphere, a three-sphere, a four-sphere. A one-sphere is a one-dimensional geometry. One-dimensional geometries just mean curves, lines, or curved curves. They're one-dimensional. And a one-sphere really just means a circle. Okay? A circle is a closed curve that comes back on itself, but an easy way to describe it is to just embed it in two dimensions, to start with a two-dimensional space, x and y, and just write the equation for a circle, x squared plus y squared, x squared plus y squared equals r squared in general. If we're interested in a circle, or let's call the radius of the circle a, if the radius of the circle is a, then on the right-hand side we would just write a squared. If we choose x squared plus y squared equals 1, we would call this a unit circle. That's the unit circle, or the unit one sphere. This is the one sphere of radius a, and that's about all we have to say about the one sphere. The two sphere you embed in three dimensions. So you start with three dimensions, x, y, and z. These are not to be thought of as the three dimensions of ordinary space. Ordinary space now is the surface of the sphere. We should learn now to be thinking that space really means the sphere itself. So a world which is a world on a one sphere would be a one-dimensional world with little bugs moving around on the circle. The two dimensions is just a crutch. The two dimensions that you embed it in is just a crutch for writing an equation whose solution is a one sphere. But the one sphere itself is a geometry, or a topology really, a geometry in which you can imagine little creatures moving around on that one sphere, and they live in a one-dimensional world. They would have no idea of off the sphere, either outward or inward. So that would be a world of a one sphere. The world of a two sphere begins again with a crutch. The crutch could be the crutch of three dimensions, which we could call x, y, and z. They would not correspond to the x, y, and z of this room. They're just a crutch. And you can guess what we would write. We would write x squared plus y squared plus z squared equals a squared. That would be a two sphere. We should call this the one sphere, unit one sphere. This would be the two sphere. Notice that it takes three coordinates, or that you start with the crutch of three coordinates, and you set the sums of the squares of them equal to the radius squared. If you write x squared plus y squared plus z squared equal 1, that becomes the unit two sphere. This is the unit two sphere. The hypothesis, or the hypothesis that we're going to investigate a little bit, or talk about a little bit, is the possibility, now this of course becomes not a circle, but like the surface of the Earth is a two sphere. It's not a reasonable hypothesis to say that we live on the surface of a two sphere. Well, actually we do live on the surface of a two sphere. It's called the Earth. But from a cosmological point of view, it's not reasonable to say that we're to think that we might live on a two sphere, but it is possible that we live in a three sphere. To construct a three sphere, oh, before I say that, let me come back to the two sphere for a moment. Again, the same kind of logic is true. We're only interested in the surface of the two sphere. We imagine that there's nothing but the surface, that the rest, the filling of the sphere and the outside of the sphere, is just part of the crutch that we use to construct the mathematical geometry, but the mathematical geometry is really the surface of the sphere. Okay, a three sphere constructed exactly the same way. I don't think I'll write it. You just invent another letter. The letter could be W. I don't want to use T because T gets, that's too loaded. It means time. But we would just make another letter, X, Y, Z, W, set the sums of the squares of them equal to a squared. That would define a three sphere. A three sphere is difficult to visualize. It's easy to picture a two sphere because you can think of the two sphere as embedded in three dimensions, but the three sphere you would have to think of as embedded in four dimensions, a little bit harder. But the mathematics is not much harder. You just add another letter to the alphabet, and you set the sums of the squares equal to a squared, and you call that a three sphere. Again, the unit three sphere is x squared plus y squared plus z squared plus w squared equals 1. Now, let me name these geometries. I'm going to call them omega. This would be omega 1, the one sphere. That's a standard common terminology. A sphere is often just referred to as omega, and this would be omega 1, the one sphere, the two sphere, the three sphere, and so forth. But we won't have much need to be thinking above three dimensions of space in any case. All right, that's one way of thinking of spheres. Another way is to concentrate directly on the surface itself, and not to think of it as embedded, and to describe it in terms of a metric, to describe the surface in terms of coordinates which are purely in the sphere. For example, the surface of the Earth would not be described by x, y, and z, but by longitude and latitude, two angles, and to represent the sphere by a metric. So let's in fact begin with the simplest case, which is the one sphere. If I take a unit one sphere, I could describe it just by an angle phi. I could describe the points along that sphere, along that one sphere, by angles phi. Now phi goes from 0 to 2 pi in this case, 0 to 2 pi. If it's a unit one sphere, we would just write that distance. We could write a metric. The metric would be very simple. If it's a unit one sphere, then metric is just equal to d phi squared. The distance along the unit one sphere is just proportional to the angle. Just to keep everything positive, I've squared it. It would just be d phi squared. Okay? That would be the metric of a one sphere. Now let's go to a two sphere. Now the way to think about a two sphere is to imagine a series of one spheres. Here's the picture. I'll draw it first with my hands. Imagine a two sphere. Okay? And think of it by starting at the North Pole. Okay, let's start at the North Pole and start with a little circle and then expand the circle and then contract the circle. So it's a sequence of one spheres where the sequence begins at one pole and ends at the other pole. Now, of course, it doesn't matter. You don't have to take the North Pole and the South Pole. You can take the East Pole and the West Pole, but or any other. I guess the East Pole and the West Pole is not the right thing, but any 2 points. But think of the two sphere. Think of the two sphere as a series of one spheres, or one sphere a series of one spheres parametrized by another angle. Now, the new angle, the angle around the one sphere still goes from 0 to 2 pi. But the new angle that goes from the North Pole to the South Pole, that only goes from 0 to pi. In other words, from 0 to 180 degrees. North Pole would be 0, South Pole would be 180 degrees, or vice versa. All right, and so here's the way to write the metric. First of all, let's draw a picture. Here's the two sphere, and think of it as a kind of series of one spheres. I've started at the East Pole instead of the North Pole. And so we introduce another angle. First of all, this phi, which goes around. But now this theta, let's call it theta, which goes from one end of the sphere to the other end of the sphere. Let's call this end theta equals 0. And let's call this end theta equals pi. All right, so let's first write let's try to write the metric now. It's not too hard to write the metric. First of all, if we move in the theta direction, along the theta direction, then ds squared is just d theta squared. If you move along the north-south direction, along the theta axis, along the theta direction from north to south, the distance that you move is proportional to the angle that you move by. But then the other term in the metric has to do with moving in the perpendicular direction being around the phi axis. This is theta. Around the phi axis, which is like the one sphere, which is like going around the one sphere, the radius of each one of these one spheres, each one of these circles is different. It's different. So each one of these is not a unit one sphere, but the radius of the sphere, the radius of the circle varies from this end where it's 0 back to this end where it's 0, but in between, what's it given by? Sine of theta. Sine of theta varies smoothly from 0 back to 0, going through a maximum at 90 degrees and then coming back to 0. So the radius of the one spheres, or the circles, the radius coming in, replacing this radius here, is sine squared of theta d phi squared. All right, so that's the familiar, and many of you are familiar with this metric. This is the metric of a ordinary two-dimensional sphere. Take any 2 points, close to each other, separated by a given interval in theta and an infinitesimal interval in theta and an infinitesimal interval in phi, and you want to find the distance between them, then the square of the distance is d theta squared plus sine squared theta d phi squared. Now, from there, you go to the three-sphere. The three-sphere is just a series of two spheres. So we imagine we have a two-sphere. Imagine now I cannot, I can't draw it easily, and I can't even use my hands properly to do it. But imagine a series of two spheres where you start with a two-sphere, you blow it up, and then you shrink it back to zero. That's a three-dimensional geometry. It takes three angles to describe it. Two to describe any one of the two spheres, but then another angle, and that other angle, or that other variable, also starts at zero, blows up, not blows up, but increases until it comes to a maximum, and then shrinks back down to zero. That's the idea of the three-sphere. And to make a three-sphere, you just introduce one more angle. Let's call it alpha. This is the three-sphere, this is the two-sphere, one sphere. And it's the unit one sphere, in fact. This is the unit two-sphere. Why don't I give it its right? Let's just call it d omega 1 squared. That's the notation that one usually writes for the metric of a unit one sphere. In the same notation, this would become the metric d omega 2 squared. That's the definition of this side. Omega 2 is really a whole sphere, and this is simply a symbol that stands for what's here. But it represents the metric of a unit two-sphere. All right, what about a three-sphere? Introduce another angle, and now I'm going to call the other angle alpha. Do exactly the same thing. Alpha varies from 0 to 2 pi, but at every point of alpha, we have a two-sphere. All right? So what's the metric? The metric is d alpha squared. Now, the radius of that two-sphere varies again, increases and then decreases, and you have to write sine squared of alpha this time, not d phi squared, but d omega 2 squared. Let me write this d phi squared. Instead of writing it d phi squared, let's call it d omega 1 squared. So notice, each time you increase the dimensionality of the sphere, you add another angle, and then you think of it as a series of lower dimensional spheres with a radius which varies from 0 to a maximum back to 0. That's the sine of alpha. You square it to get the metric. And then you write the metric of a unit one-dimensional less sphere. This would be ds squared for the three-sphere. Let me write it out explicitly just to make sure that you understand exactly explicitly what this means. It means the alpha squared for the s squared for the three-sphere is equal to d alpha squared, that's the extra angle we add, plus sine squared of alpha, and then open up a box and just write the previous metric of the lower dimensional sphere. And just call this thing here d omega 2 squared. All right, you can go on with this. I'll tell you what the general answer is. The general answer is, if you want the d-sphere, for example, the four-sphere, we just write the same thing, d alpha squared plus sine squared alpha times the metric of the three-sphere. of the unit 3 sphere. And so by induction, we can go to the metric of any dimensional sphere. But we'll never need more than the 3-dimensional sphere unless during the course of this lecture series an announcement is made in the New York Times that it is discovered that the world is 4 or 5 or 6 dimensional. Well, they do that all the time, but not in the sense in which I mean. Okay, that is the idea of a higher dimensional sphere. Once you think of it this way, you can forget the crutch of how it's embedded in the higher dimensional space. Notice that the one sphere is described by one variable, one coordinate, phi. You don't need x and y. The 2 sphere is described by 2 coordinates, theta and phi. Well, okay, this is d phi squared. The 3 sphere by 3 coordinates, and we've lost all memory of whether or not this sphere is embedded in the higher dimensional space, and we will consider it not to be. Just an abstract description of a geometry. Now this geometry has special features, as I said. It's uniformly curved. It's everywhere the same as at every other point. For example, there are other kinds of geometries that we could but describe, which would have different metrics, perhaps some simple deformations of this metric. Put some wrong coefficient, some other coefficient, or put some other function besides sine squared theta, which still goes from 0 back to 0. You'll be making some sort of deformed sphere. For example, you could make an ellipsoid. An ellipsoid is a very nice surface, all right, but it's not uniform. It's different at some places than at other places. It has places where the curvature is larger and places where the curvature is smaller. The sphere is rather special in that it's uniform. Wherever you are on the sphere is the same as at every other point. So it's called homogeneous, just like a cosmology. Okay, now these are unit spheres. Each one of these is a unit 3 sphere, 2 sphere, 1 sphere. Supposing we now want to make a sphere of radius a, the metric of a sphere of radius a, then all we have to do is take the metric of the unit sphere and multiply it by the square of the radius of the sphere. Why the square? The square because the metric here is associated with the square of the radius, or the square of a distance. And so if we actually wanted let's say a 3 sphere of radius a, we would take this whole thing and multiply it by a. All right, so we would write squared. Thank you. A squared. Okay. So we can write it this way. We can write that ds squared for a sphere of radius a is just equal to a squared times d omega. And let's now fix ourselves to the 3 sphere. But it doesn't matter, whatever dimension we're talking about. 3, 4, 5, 1, 2. Incidentally, what is a 0 sphere? 2 points. Why is it 2 points? Let's just for fun, let's ask what a 0 sphere is. It seems like a stupid idea, a 0 sphere. I mean, a 1 sphere almost seems sort of silly. It's just a circle. A zero sphere is 0 dimensional. All right? But the way to figure out what it is just to extrapolate this formula back 1 step. So if a 1 sphere is x squared plus y squared equals a squared, and a 2 sphere is x squared plus y squared plus z squared equals a squared, then a 0 sphere must just be x squared equals a squared. Or let's take the unit 0 sphere. The unit 0 sphere is x squared equals 1. What are the solutions of x squared equals 1? Plus or minus 1. All right? So a 0 sphere is just 2 points. Now notice it's kind of interesting that the one sphere can be made from the zero sphere by taking a sequence of zero spheres. Here's the first zero sphere, here's the next zero sphere, here's the next zero sphere, here's the one of maximal radius, and then we come back to the zero sphere, which is small. So now don't ask me what a minus one sphere is. That one I can't do. But I'm sure that mathematicians have a definite, well, I'm not sure. Actually, I've never heard of a minus one sphere. I've heard of a horn sphere. Have you heard of a horn sphere?
It's the boundary of the zero sphere.
What is? A horn sphere? Nah.
Minus one sphere.
Oh, minus one sphere. Yeah, that's the yeah. Yeah. Negative dimensions is never interesting. I don't think it is. Fractional dimensions is sometimes interesting. Okay. Now let's think about cosmology. And let's think about the cosmology of a world where space is a three-sphere. We're not interested in space now, we're interested in space-time. And what this space-time is describing is a space of variable radius, a space whose radius changes with time. The Big Bang theory, for example, could be considered a theory in which the world is a three-sphere which starts out extremely small. How small? Well, let's say the Planck size, or some arbitrarily small size, even zero, and expands and expands and expands and expands. It may or may not come back and implode on itself. We're going to talk about that. But don't get the idea that we're thinking in any sense about a higher dimensional sphere when we embed it in time. Time is different. Don't try to conflate time with one of these dimensions here. Then you get in trouble. Okay, so let's talk about the cosmology and the metric of a geometry of an expanding or contracting or time variable sphere. Well, all we have to do, well, we first write down proper time now. This is the space-time interval. The space-time interval is the proper time, just as in special relativity. And as always, it starts out with a positive term, dt squared, which we can take to be just dt squared. You can change variables. For example, you can take some other function of the time so that there would be some coefficient in front here, but there's no particular reason to do that. It starts out with dt squared, and then that's the metric associated with the clock. This is the thing which reads off clock time, and then minus the space metric, which is a of t squared, the time-dependent radius of the spherical universe, times d omega 3 squared. Now let me say one more thing about these coordinates. As I said, there's nothing special about any particular point on the sphere. Let's draw a two-sphere. For the two-sphere, we would write the two-sphere exactly the same way, except instead of putting d omega 2 here, we would put d omega 1 squared here. That's the only difference. Okay. It's convenient, it's convenient to focus, as I said, on one of the poles of the sphere and think of it as the place where we are, us, where we are. One of the poles of the sphere. In other words, to coordinatize the sphere in such a way that we are at the North Pole. Now, there's nothing special about that North Pole, and presumably there's nothing special about our own location. It's just a definition of where we are. We are at the North Pole of the sphere. That means we are, I guess the North Pole is over on this side. I'm sorry for the fact that north isn't vertical, but that's also an arbitrary tradition that somebody invented in the past.
That way they do it in Russia.
Well, the reason I did it this way is because, yeah, it's usually the case that we put the North Pole at the top, but we also usually measure angles from the horizontal. So I had to compromise somehow, so I put the North Pole over on the right. North Pole, South Pole over here. Okay, what was my point? My point is here is, so as a convention, no real invariant significance to this, but we are over here, us, the US, us. Okay, we're over here. And that means that alpha, which measures distance, which measures angle away from us, can be sort of thought as a radial distance away from us on the unit sphere. It's not the radial distance measured in kilometers or any other units, but it's the measure, a dimensionless measure on the unit sphere. And it can sort of be thought of as radial distance. Here's lines of fixed radial distance from us. So alpha can be thought of, and it's useful to think of it as distance from us, or a coordinate which represents the radial coordinate away from us in space. Okay, so here we are. Here's the metric. We can plug in d omega 3 times a of t squared. The only difference now between this and this is that a is time dependent and represents the time dependence of the radius of the universe, if you like, the spatial radius of the universe. This geometry, and it's very simple, that's all there is to it. I mean, of course, it is more complicated than that in a certain sense. Just as the Earth is full of little irregularities and so forth that would make the metric of the surface of the Earth quite irregular, so too is the universe irregular because of the presence of galaxies and stars and other lumpy things. But apart from those small lumps, this is all there is to the metric of a universe which is spherical, spatially spherical. This is called, well, the geometry, both the geometry and the cosmology based on it is called Friedman, Robertson, Walker, and some people put an L in there for Lemaitre. I got used to calling it FRW, and I will not speak the names of any of those people, because if I speak the names, I will leave out one important one, Lemaitre. It's just, everybody just says FRW. So it's an FRW universe with spherical spatial shape. Okay? It has positive curvature, not positive space-time curvature, positive spatial curvature. Right? To indicate that it has positive spatial curvature, we sometimes write that it has k equal to +1. Now, what is it that's +1? Nothing is +1. It's just, this means curvature positive. Okay, that's all there is to the geometry of the sphere. But I want to describe spheres a little more. I want to give you a little further picture of thinking about spheres, and especially looking at spheres and looking out at the world around you from the North Pole, so to speak. Maybe I'm looking out at the world from the South Pole. Yeah, I have a feeling in my drawings I'm going to put us at the South Pole. Now I'm really going to put the South Pole at the bottom. Why is the South Pole at the bottom and the North Pole at the top?
Because people from Northern Hemisphere are drawing the map.
No. It's because if you take a map and you turn it upside down and you draw it upside down, just do it, and you'll notice that South America is sort of unstable. South America hangs from North America. North America doesn't hang from South America.
A very bright friend of mine used to think that all rivers ran north and south, and he was thinking of the Nile.
Look, I have a friend who's about a famous physicist who had two beliefs in his life. One of the beliefs is that no matter what direction he was driving, it was always north. The other thing that he believed when he was young was that cats were female dogs. I'm going to tell you his name. His name is Willie Fischler. He was a good friend of mine. He's probably not after he sees this. Yeah, FRW, this is an FRW K equals +1 universe. Means positively curved and of this special kind. Now let's talk a little bit more about spheres. When you make a map of the Earth, you would like to lay the map out on a flat plane. And you'd like to do it in a nice way that preserves shapes and so forth. There are various ways to do that. There's Mercator projections and other kinds of projections that project the sphere onto the plane. They always distort sizes. You can't stretch the sphere out onto a plane without distorting it. But there's one particular mathematical construction, which is probably the nicest mathematical construction. It's not good for cartographers. And the reason is it requires an infinite plane to draw the surface of the Earth in a stereographic projection. So let me show you what a stereographic projection looks like. And it is somewhat useful to draw this because when I get to the negative curved side, about all I'll be able to tell you about it to draw it will be to draw the analog of the stereographic projection. All right, the stereographic projection is done in the following way. Here's the mathematical construction. You can do this with a sphere of any dimension, incidentally, but let's take a two-sphere. So here's a two-sphere. If it's a two-sphere, I'm not going to bother drawing lines of longitude and latitude. It is a two-sphere. It's not a one-sphere. And think of it as resting on an infinite plane with the, I guess we'll call it the South Pole, with the South Pole tangent and just touching the plane. All right, now, I want to construct a mapping from the sphere onto the plane, from the sphere to the plane, so that every point on the sphere is represented uniquely by a single point on the plane. And there's an easy way to do that. It's going to have a bit of problems about the North Pole. But apart from the North Pole, every point will be located on the plane in a unique way. And the way to do it is to, let me see if I have some colored chalk here. Go pick a point, any point at all on the sphere. Go to the North Pole and draw a straight line. Now this is not a straight line, which means it's not a geodesic in the sphere. It is really in 3 dimensions. Draw a straight line from the North Pole to the point and continue it till it hits the plane. Identify this point on the sphere with the corresponding point on the plane. Every point on the sphere will be represented by a unique point on the plane. The South Pole of the sphere will be right at the origin of the plane. It's just the North Pole of the sphere which is going to have a bit of problem. As you go out to the North Pole, as you get closer and closer to the North Pole, the image on the plane moves out moves out to further and further and further away. Okay? In fact, if you approach the North Pole from different directions, the image on the plane goes way, way out to infinite distances in a way that remembers the direction. This point very close to the North Pole over here has its image way out over here. The point over here has its image way out over here. So the North Pole has a little bit of difficulty, and mathematicians have a way of dealing with it. They simply say infinity is a single point. They say infinity, we'll just call it the point at infinity. What we really mean is the North Pole of the sphere. Okay, now let's draw some figures. First of all, let's draw Antarctica. Antarctica is down here, and this is in the approximation of a perfectly circular Antarctica. Here's Antarctica. It will look like a little, let's redraw it over here on the plane. Here's the plane, looking at the plane head on. Here's Antarctica. Antarctica simply looks like a little circle. Now, of course, there's the Arctic Circle up here, or the North Polar ice cap, which still exists a little bit. The North Polar ice cap looks entirely different. It's way, way out far. I didn't give myself enough room. It's way, way out far like that. And as you get closer and closer to the North Pole, as the North Polar ice cap shrinks, this circle will get bigger and bigger. Okay. But imagine that the North Polar ice cap is actually the same size, really, meaning on the real Earth, or on the real sphere, is the same size as here. So there's clearly a distortion of sizes. Let's put another continent over here and a continent over here, which by assumption in this model world here has the same size. All continents have the same size as Antarctica. Well, when we draw them on the plane here, the Antarctica will look like the smallest one. As we move away, they'll look bigger. As we move to continents which are close to the North Pole here, they will look gigantic. So the further out we go, the bigger these things will look on this plane. Now, straight lines or geodesics that emanate from the South Pole here, those are just great circles. Those are just great circles and lines of constant longitude. They look like straight lines here in this picture. They just look like this. And they're characterized by a angle of longitude. Now, the main thing I want you to notice now, and which is more or less obvious, is that if you were at the center, let's put us at the South Pole now, this time we're at the South Pole, and we're looking out around the world, we see angular sizes which are distorted relative to the size of the object. In other words, this object over here looks too big to us. When we look at it, it subtends too large an angle compared with flat space. Compared with flat space, this object will look too big to us. Right? What's actually happening is that, well, what's actually happening is that the sums of squares of the sums of the angles of a triangle is bigger than 180 degrees on a curved surface like this. And so if we were to draw triangles here, the angles would be bigger than they would be in flat space. But from the point of view of an astronomer looking out, let's suppose that that astronomer was looking out at a structure out there which he happened to know was the same size as our galaxy. For some reason, he sees a galaxy out there which looks very similar to our galaxy, has the same kind of structure, has good reason to believe that that galaxy is very similar to our own. When he looks at it, he will see an angle in the sky which is bigger than he would see if the space was flat. All right, that's something to keep in mind, because that's basically the way we determine whether space is curved or not. Right? By looking at angles of things whose size we think we know. Now, it's not galaxies. Galaxies are not good measuring rods. First of all, we can't, not for deep cosmic distances. But there are other objects that we can detect, whose size we have reason to believe we know, and whose angle in the sky we can detect. Yeah, and we have to know the distance too. Yeah, we have to know the distance too. Right, so knowing the angle in the sky is not sufficient to tell you anything. You need to know the angle and how far away you are.
And another
In
question.
fact, how far away they were when they...
And that's exactly. Well, turns out that cancels out, but question.
Another question, do circles on the surface of the sphere project as circles?
Yeah, they do.
Circles and not...
No, circles. Circles. It's one of the nice things about. Okay. Yeah, circles project to circles. That's a feature of stereographic mappings. Yep, all circles. It's obvious for horizontally oriented circles. Not so obvious for other circles, but it's true. True anyway.
So that means a continent would have the same, or would it not have the same shapes, a non-circle?
Okay, there's two statements, both of which are true and slightly different. First of all, it is true that circles project to circles. Okay, that's it. But if you're talking about arbitrary shapes, then there's a weaker statement, but still a true statement. The weaker statement is small things, and now you have to think about differentially small things, but small objects will have the same shape. Same shape means same ratio of sides and so forth. So this is a shape preserving, at least for small shapes. It's a shape preserving mapping. Angles are preserved. Angles, perfect. Angles are preserved. Yeah. There's a word for angle preserving, conformal. This is a conformal mapping. Not all conformal mappings preserve circles, incidentally, but this one does. It's conformal. The Mercator projection is also conformal, and so continents have the right shape, as long as they're not too big, they have the right shape, but they have the wrong relative size. Same thing here. Okay, that's about everything we need to know about spheres. Now let's spend a little time with I call it the opposite of a sphere. It's not the opposite of a sphere. Another geometry which has negative curvature. And I'm going to tell you how to construct it. I'm not going to derive this. I will tell you what the metric is for a negatively curved analog of a sphere. And then I will draw you the analog, not of, we can also do the stereographic projection, but I'll show you what the stereographic projection or the analog of the stereographic projection looks like. And I will assign it as a homework task to be turned in next time when I'm gone, incidentally. I better tell you right now. Back to England. Next week. Next week I'll be gone. But then I'm finished. I am not going anywhere after that. Not for a while, anyway. This was just very, very bad timing. I wasn't watching what I was doing, and I answered some emails too quickly and said yes, and I didn't realize they were all within weeks of each other. Italy, Russia, England, and back and forth like a nutcase. My doctor said, "You're crazy, you're going to kill yourself. If I'm dead, hold the class anyway." Yes, all right, negative curved space. All right. First thing about negative curved space, well, all right, let's not go, let's do the first thing last. Yeah, the metric of a negatively curved space, uniform negative curvature. It's pretty unique. It's pretty unique, much like the sphere. Uniform negative curved space, and it's related to the metric of the sphere in an extremely simple way. In every dimension, whatever dimension, let's write the general formula for the sphere first. Sine alpha squared times, times d omega of one less dimension, d minus 1 squared, that's d omega d squared. Is this clear what this means? That you take a sphere of one less dimension. You know, capital D is usually reserved for space-time dimension. But I don't mean the space-time dimension here. I mean just the space dimension.
You don't like n?
I don't mind n. You want me to write n? Sure, n. I don't care. It doesn't matter. It doesn't matter. It's a correct formula no matter what we call the thing here. All right, so this is the way you go from one sphere to the next. The negative curved version is called the hyperbolic plane. What it has to do with hyperbolas, don't worry about. Maybe I'll get a chance to tell you what it has to do with hyperbolas. But the hyperbolic plane is the analog of the sphere with negative curvature. And I'll tell you very simply how to get it. You replace the sign of alpha. You don't change this. You don't change this, okay? But you change the sign of alpha to something else. What you change the sign of alpha to is the hyperbolic sign of alpha. This is not a sphere anymore. Furthermore, one other thing. The sine function, of course, really is a function of an angle, typically.
Call that d omega?
No. We will call this is d omega. I'll tell you why in a moment. But this is now not called d omega d, but it's called d script h d squared. The h stands for hyperbolic. And it's not as universal a notation as this is, but it's called the hyperbolic plane. All right. Now, one important difference is in this formula, alpha goes from the North Pole to the South Pole and varies between 0 and pi. In this formula, alpha goes from 0 to infinity. Sines are periodic functions. They come back to themselves, or at least sine being 0 comes back to itself after alpha becomes equal to pi. So you shrink, you start from 0 size and you go back to 0 size. The hyperbolic sign is not a periodic function, and alpha just goes from 0 to infinity. Okay. Right. Goes from 0 to infinity, number one. I'm going to write down what the meaning of hyperbolic sine is for those who don't know. It's a very simple function. The sine, the hyperbolic sine of a variable alpha, which is not an angle anymore, it's not an angle anymore, is just by definition e to the alpha plus e to the minus alpha divided by 2. What? Minus. Thank you. I would have made that mistake. Minus e to the other. It's the analog of the statement that sine of alpha is e to the I alpha minus e to the minus I alpha over 2I. All right, but we don't particularly need this formula here.
So, I'm sorry, in the metric for the data curve space, is that lower dimensional differential via D's?
Where are we? Sorry, which blackboard are you on?
The differential associated with sine, hyperbolic sine?
Here?
Yeah, over there, the differential that you're promoting to the, yeah, right there.
This side?
It's spherical.
D minus 1.
D omega. Is that omega or H?
This is correct.
Should that be a D?
That's spherical there, is that right?
Yeah, that's a regular sphere. All right, I'll tell you what's going on here. And we'll get to what's going on. I'll explain what's going on in a moment. But let me just tell you the mathematical facts, and then we'll think about what they mean. Okay. Alpha goes from 0 to infinity. When alpha is 0, the hyperbolic sine is 0, so is the ordinary sine. These two cancel for alpha equals 0. So the hyperbolic sine begins very much like the sine, but then instead of turning over and coming back to 0, it exponentially increases. E to the minus alpha, when alpha gets large, e to the minus alpha gets very small, so this is negligible, but e to the plus alpha grows. And so for large alpha, this is basically just e to the alpha over 2, and it just grows. All right? So one of the things that's saying is that the size of this, think about the sphere first. As the angle alpha increases for the sphere, the lower dimensional sphere grows and then shrinks. Grows a little modestly, stops growing, and then shrinks in the mathematical sense. Here, as you move away from the origin, as you move away from us, again, we'll put us at the center, us at alpha equals 0. As we move away, the size of the spheres around us get bigger and bigger and bigger very rapidly. Right? So think of ourselves at the center. If we want to know the distance to a point radially outward, that's mainly just d alpha squared. That's d alpha. That's this part here. But if we look around us at the sky, what do we see? We see a two-sphere. The sky is a two-sphere. It's described by two angles. But the size of that two-sphere, in the spherical case, the size of the two-sphere, as we look deeper and deeper into space, gets bigger and then gets smaller. Here, the size of the two-sphere grows very rapidly. So as we look out far away, the size of the sphere that we see is exponentially growing in this geometry here. This is the definition, or it's not the definition of the hyperbolic plane, but for our purposes, this is the definition. But I'm going to draw you a picture of what it looks like. Now, if you want a much better picture than I can draw, there's a very famous picture of the hyperbolic plane. It's the one I like best. It's Escher's drawing. And just look this up on, just plug this into your Google, MC Escher, and the drawing is called Limit Circle Number 4. IV. Studying that picture will tell you more about cosmology than any of these equations, or at least the cosmology of negative curved spaces. But I'm going to do my best to draw something that looks, roughly speaking, like Escher's drawing. This is sometimes also called Angels and Devils, but Angels and Devils is a different drawing. It's a bunch of, only Escher can do these things. But what it is, all right, you start with a disk. Now what this is it's actually the analog of the stereographic projection. The stereographic projection here goes out to infinity. The North Pole is, although the North Pole is really not very far away, on the stereographic projection it looks like it's very far away. And every continent appears to get bigger and bigger as you move further and further away. Exactly the opposite is true for the negatively curved spaces. What looks like it's not very far away is infinitely far away. Okay? And the continents, which are, or galaxies or whatever they are, let's call them continents, all of which by assumption have the same size, look smaller and smaller as you go away. So Escher doesn't draw continents, he draws angels and devils in some devilishly clever way. The first devil is about, the one near the center is about that big. And then you move out a little bit, and the next set of devils or angels are about that big. Now, they really are the same size in the same sense that Antarctica is about as big as what? Australia, maybe? I don't know. But of course, Australia looks much bigger on this type of projection. Okay? Here, Antarctica has a certain size, but Australia, which is the same size, and now there are lots of Australias around here, more potential places for Australias. Here there's a certain number of possible places for Australia. Here there are more places because the sphere, the two-sphere, is getting bigger and bigger, exponentially fast. The next layer of continents looks even smaller. And the next layer looks even smaller. I'm going to draw half of this and throw the other half away because I get tired of drawing it. And as you get closer and closer to this boundary, which is not really a boundary, they look smaller and smaller and smaller. Well, each one of these continents is the same size, geometrically. So that means if you want to know how far it is from the center to the boundary, all you have to do is count the number of continents that you cross. But the number of continents that you cross is infinite because they get smaller and smaller and smaller. So the distance to the boundary, although in this picture it looks like the distance to the boundary is finite, whereas in this picture it looks like the distance to the boundary or the North Pole is infinite, it's really quite the opposite. Really, the North Pole is not very far here. In fact, if you counted continents, because they get bigger and bigger, you would pass a finite number of continents before you got out to infinity. Here, it looks like the end of the world is not very far away, but if you count continents, there will be an infinite number, and so this is really an infinite geometry. This is really an infinite space with an infinite volume. This space has finite volume. But one thing which is common for both of them is that they are homogeneous. This doesn't look homogeneous. It looks like these continents have different size than this continent over here, but in fact we know from the fact that it really is a sphere, we know that every point is the same as every other point. It's not obvious, but it's also true here. Every continent is like every other continent. That means that there are symmetries of this figure where you can move this continent to here, this one will move to here. There are symmetries which are the analog of rotations of the sphere, for example. Rotations of the sphere will move the South Pole to here, something else will come and take the place of the South Pole. There are symmetries of this figure which move the South Pole out to some other place over here, and meantime they move some other place to the South Pole, and the whole figure shifts, but the geometry, the intrinsic geometry of it doesn't change. So this is again a homogeneous space of uniform curvature, but if you were to calculate the curvature, you would find it's negative. Now, a question you might ask is, incidentally, I've drawn the case of H2, 2 dimensions. I cannot so easily draw H3, but it's made the same way. You take a 3-dimensional ball and you fill it with smaller balls, first this one this size, and you just make a 3-dimensional version of this. It's not too hard to figure out what that means. You make a 3-dimensional version, a ball at the center this big, balls surrounding it on all sides which are smaller, more balls surrounding it which are yet smaller, and so forth. Same pattern, and that would make H3 for you. This is H2. Now I forgot what I was going to say about it. I was going to say something else about it, but I don't remember what it was.
So an observer in any one of those circles would see a similar pattern.
Would see what?
A similar pattern?
Yeah, they see exactly the same thing. Exactly the same thing. And it is very, very instructive to take Escher's drawing and just look at it for a while. Yeah.
As you look out on the spherical case, things seem to be bigger than they are.
Right. Here they're smaller. Yeah, this sphere is the same size as that sphere. Okay? That means if a telescope was pointed at the 2 extremities of this galaxy over here, I'm going from galaxies to continents to angels and devils, but all the same stuff. If you were to point your telescope and see what the angle subtended, you would tend to see a smaller angle than you would in flat space. So again, if you knew the size and the distance of some object out here, in the positively curved space, it would look too big. Now, 2 means relative to flat space. And in negative curved geometry, it would look too small. All right, so that's basically the way that we tell whether space is curved or not, by looking at those angles. Yeah.
Is the relevance of the stereographic projection that the astronomer can construct those from the observations? Is that the...
Yeah. Yeah, I mean, an astronomer can construct it from the observations. And it turns out that you say, do you have to fold in the fact that it changes with time? Whether you have to fold in the fact that it changes with time. In fact, no, you really don't, but that's a separate issue. Let's forget for the moment the fact that it's time dependent. Yeah, the astronomer is a surveyor who surveys triangles in the sky and measures angles.
But, I mean, it's not usual for surveyors to create stereographic projections of things, but that seems to be what...
That's because surveyors usually survey small portions of the surface of the Earth. And so the overall curvature is not important. If we were in the business of surveying large pieces of the Earth, well, we have our choice. Of course, we could build ourselves a globe, but if we wanted to put it on a flat page, we would have to do some sort of projection. What's it called? The Mercator projection is a nice one for maps, but for those self-centered people who like to think of themselves at the center of the universe, this is better. The In other words, for astronomers who literally look out around them, and they do want to prejudice their drawings by putting themselves at the center, then the stereographic projection is more convenient than the analog of the Mercator projection. Okay, so that's the mathematics of negative, well, the intuitive mathematics of negative curvature. Keep in mind that although the projection of the sphere looks infinite, it's really describing the finite sphere, whereas the projection of the hyperbolic plane looks finite, it's really describing a space which is infinite. All right. Cosmology based on space, which has negative curvature, is usually called infinite FRW, infinite negative curved FRW. So, what does infinite negative curved FRW look like as a mathematical metric? Same deal. d tau squared is equal to dt squared minus, again, some natural radius of, some natural size of the thing times dh3 squared. Let me draw one more way of thinking about the negative curved space. You cannot take the whole negatively curved space and embed it in three dimensions. Let's take the two-dimensional case. The two-dimensional sphere you can nicely embed in 3 dimensions and draw it. You can't do that for H. It just doesn't fit together right. But small patches of it you can draw. A small patch of it you can draw. You just can't fit it all together. And what it looks like is a saddle shape. It's the saddle surface. The saddle surface is the negatively curved space. So you could take small patches of it and redraw them as embedded in three-dimensional space, but you simply can't fit them together to form the whole hyperbolic plane nicely. Okay, that's the hyperbolic plane. Here's Friedman, Robertson, Walker, or FRW. I promised not to use the names. FRW. But now it's not k equals plus 1. It is k equals minus 1, simply meaning negative curved space. Okay. We will attach that number, k equals plus 1 or minus 1, to these two cases. Then there's one more FRW geometry, which also, there's one other kind of homogeneous space. We have two kinds of homogeneous space, positive curved for the sphere, negative curved for the hyperbolic plane. There's one more case which sort of sits just between them, the dividing line. The dividing line between negative curved and positive curved is flat space. Flat space can either be thought of as the limit of an infinitely big, well, just think of it as just flat space. Let's not think of it as any limit. Just flat space. For that, d tau squared is just equal to dt squared minus a of t squared times dx squared plus dy squared plus dz squared. Good old flat space. Ordinary flat Euclidean space. This, though, representing the tendency for things to separate, so to speak. This would be the metric of FRW. And what would you put here? K equals 0. Okay, these are the three. Of course, these are not the only possible cosmologies you could think about. These are the three homogeneous cosmologies. And they are sort of the classic three cases. All right, are there any questions about the geometry of these things up till now? Yeah.
Yeah, if you would project, like do the projection of either one, either the positive or negative, onto a plane, and you were tracking like a signal on that continent, the projection of it, you watch a light go from Perth to Sydney and you project it. On the projection, the velocity of the light would tend to be transformed as well.
Yeah, well, for example, yeah, I think I know what you're saying, and I think you're absolutely right. On the projection, for example, let's first of all completely forget the fact that the universe expands for a minute. Just take it as a fixed radius. Then, of course, on the sphere, it takes a finite amount of time for a signal to go from the North Pole to the South Pole, but which is true in general, but on the projection, the North Pole looks like it's an infinite distance away. It's not really an infinite distance away. It's just an infinite distance on the image. So that must mean that light rays, when they move, go faster and faster the further out you are. Okay, and that's true. Not that they don't really go faster and faster. They just go faster and faster on the diagram because a given amount of ordinary distance corresponds to a larger distance on the projection. Here, light rays go slower and slower. Not really, but in the figure. Because it has to take an infinite amount of time for them to escape to an infinite distance. So the only way that can be is if on the drawing, on the projection, it will look like light rays go slower and slower. Okay, I think that's what you were asking. Yeah, right.
Have you used looking at objects far away to determine the flatness?
Yes. Well, it's really angles at the, no, because you can't get, not easy to find out how fast light is moving out there. Look, measuring distances is let's come to it. That what you said is true, that the speed of light as measured on the projections varies from place to place. Is it particularly useful? It probably is. I just can't think of an example right now. What I wanted to get to, but I think I would like to rest for about 5 or 6 minutes. Take a little rest for 5 or 6 minutes, and then I want to come back to the connection. Now we're set up to talk about the connection between the Newtonian equations of cosmology that we've used over and over. We've called them the FRW equations, and the general relativity of these different metrics. So let's take 5 minutes and take a break, and then come back. I'd like to finish up tonight by just discussing the connection between equations that we've already seen and Einstein's equations, which I didn't want to do earlier because in order to understand the full impact of general relativity, it's important to understand these three cases and to combine them together to see the point. Before I talk about Einstein's equations, a very, very brief review of the Newtonian version of cosmology. I'll just remind you of how we thought about it. We said again, put ourselves at the center, look at a galaxy moving away from us. Let's put it on the x-axis just arbitrarily. Look at a galaxy receding away from us according to the Hubble law, and look at the Newtonian equations describing the motion of that galaxy moving away. What we said was the only mass which contributes to the gravitational pull on that object toward us is the mass contained within a sphere. That's Newton's theorem. Newton's theorem says that for any spherically symmetric mass distribution, the only force on an object is the force of the material inside the sphere at radius equal to the distance of the object itself. So we simply said all we have to do then is imagine all the mass in the sphere is concentrated at the center, M, all the mass within that sphere, and then write Newton's equations for this object moving away. Obviously, again, there are three possibilities. The first possibility is that it's moving away with a velocity larger than the escape velocity. Then it'll just continue to go. Less than the escape velocity, in which it will turn around and fall back toward the center, and exactly at the escape velocity. So again, there are three cases. Now, there was also other divisions. If we simply talked about ordinary non-relativistic matter, in other words, galaxies which were flowing with the flow, then we wrote that the energy density, we wrote things in terms of the energy density or the mass density, that the mass density rho went like the mass divided by a cubed. There were other possibilities. If it was radiation in here, then the energy density would be, would go as 1 over a to the 4th. And we also talked about vacuum energy. Vacuum energy was a component to energy which didn't change as the sphere changes. But that was the basic setup. Newton's equations applied to a galaxy. And you apply it to any galaxy anywheres, and you get the same equation of motion for A. But in particular, the energy conservation equation, just ordinary energy conservation for this object, can be written in a very simple form. The kinetic energy was just proportional to a dot squared. This distance is proportional to a. The distance to any given galaxy is proportional to the scale factor. So the kinetic, I won't write the details, I'm just reminding you now, there was a term a dot squared, then there was potential energy, and the potential energy we put on the other side of the equation was some potential energy, and I'll just remind you what the equation looked like. By the time we manipulated it a little bit, we divided it by a squared and eventually got on the right-hand side the energy density, rho, or the mass density. The mass density on the right-hand side, let's put it back. It goes this way. But then there was another term on the right-hand side which we set to 0. It had to do with what the energy of the outgoing particle was, what the energy was. If the energy could be greater than 0, less than 0, or equal to 0. The case that we studied was the case where you were right at the escape velocity. If you're not right at the escape velocity, there's another term here, which is just the total energy, a constant, and the way that it came into the equations was on the right-hand side, some number, which I don't remember what I called it. I may have just called it k. Let's call it some number divided by a squared. It looks a little bit fun. Let's put the. Shall I go over that, or does everybody remember it well enough? Everybody remembers it? Okay. Okay. This was the basic equation of cosmology. We left this term out. Well, there's no good reason to leave that term out, although empirically it is known to be very small. So as an empirical fact, it's a good approximation to leave it out, but as a conceptual thing, there's no reason to leave it out, and we should come back to it. But in order to come back to it, we really do need to think about Einstein's general theory of relativity. which we're not going to do in detail. We studied it in some detail last quarter. I'm just going to tell you the results of calculations, and you can fill in how you do them. By now, you should know enough to be able to do them, but they'd be a little bit tedious. Not too. Okay. We start with the FRW form for the geometry. Let's take the case of the sphere first. Let's take the top case, the sphere first. Okay, we start with that type of geometry. The only unknown in it is A of t, but when I say an unknown, I mean a time-dependent unknown. In other words, there's an unknown function in there. Maybe it's known or not unknown, but it is the dynamical degree of freedom. It's the degree of freedom which tells us how the universe expands and so forth. So we take that form with a general function A of t. And then we're going to impose Einstein's field equations and determine some information about A of t. Now, we're not going to actually do it. I'm going to tell you what happens when you do it, though. So let's start with Einstein's field equations. I'll just remind you what they are. They involve the curvature tensor. And in particular, they involve the Ricci tensor, R mu nu, minus G mu nu. Now, you're not going to need to know the details of this. If you haven't studied general relativity, I'll tell you the facts. But I'm writing this for those who have followed the previous quarter. Anybody remember what this tensor is called? R mu nu is the Ricci tensor. It's made up out of the curvature tensor. G mu nu is the metric, except the inverse metric, and R is the Ricci scalar, is the curvature scalar. And this is a four-dimensional now. This is now the four-dimensional space-time curvature tensors. Anybody remember what that's called? It's called the Einstein tensor, and it's usually written G mu nu. But the important thing is it only involves the geometry. It's a thing which involves geometry, and it involves the curvature of the space-time geometry. Not the spatial geometry, but the full space-time geometry. That's the left-hand side of Einstein's equation. So the left-hand side, space-time geometry. Right-hand side is the sources of the gravitational field, and those were energy and momentum. The energy momentum was summarized in terms of another tensor called the energy momentum tensor. All right, so on the right-hand side, we have the energy momentum tensor T mu nu, and I think there is, let's see, I think there's a 4 pi Newton's constant there, if I remember. So just a few words about what's on the right-hand side. Oh, and mu and nu go from zero, or go from over 4 possibilities, x, y, z, and t. So this is 4-dimensional space-time geometry. And there is an equation like this for each mu and nu. Those are the Einstein equations. How many are there altogether? Mu and nu can go from 1 to 4, so 4 times 4 is 16, but the tensor is symmetric and it has some symmetries. How many equations? 10, I think there are 10 equations altogether. 10 equations altogether. But we're only first of all, we only need to know about one of them. The right-hand side, these are the components of the energy momentum tensor, which mean things like energy density or mass density, depending on whether we want to use E equals mc squared to relate energy to mass, and no reason why we shouldn't. When c is equal to 1, the right-hand side contains things like energy density and momentum density and so forth. We're only going to need one of these equations. The reason we're only going to need one of these equations is because we've already assumed so much about the structure of the geometry. There's really only one unknown. Now, of course, we've assumed an enormous amount. We've assumed that the geometry is homogeneous. We've assumed that the space is a sphere, and so we've made a lot of restrictions on the nature of the geometry, and so we really only need one differential equation, one equation to tell us how A varies. What's the natural one to pick? The natural one to pick is the one with both mu and nu equal to time components. So you can do that. You can write down that R00 minus G00R is equal to 4 pi G. And what's T00? The energy density. It's the energy density. We've already called that, we've already named that rho. The right-hand side is energy density. The left-hand side is geometry. Okay. All right. Next, we want to calculate, we're not going to do this, but in principle, you know how to do this. You calculate the energy momentum tensor from the metric by differentiating it a couple of times, calculating Christoffel symbols, doing whatever it is you're supposed to do to calculate the curvature tensor. If necessary, you go look up in a book what the curvature tensor is for a geometry like that. And here's what you find. You find there are two kinds of terms. The first kind of term has to do with the fact just that the geometry is time dependent. It would be there even if space was flat. If space was flat, but the scale factor was time dependent, there would be a space-time curvature. Not a space curvature, but a space-time curvature. And if you work that out, spend a little bit of time with it, you find that these two terms combine together to give you, I will figure out the coefficient later. There's a numerical coefficient. I'll figure it out later by knowing the answer. But it's proportional, guess what, to A dot over A squared. So if you work out for the flat space case, the flat space means flat space, not flat space time, k equals 0, the k equals 0 case, you take that metric and plug it into the formulas for curvature, calculate R naught naught minus G naught naught R, and you will get A dot over A squared. Okay? So the first thing you'll find is for the flat space case, k equals 0, A dot over A squared is just 4 pi G rho. And of course, that's not quite right. If we actually did the Newtonian calculation, we would have gotten 8 pi over 3 here times G rho. And so that leads me to believe that when you actually carry out this calculation, that the Einstein tensor here is 3/2 of this. Many years ago, I checked this. I've never checked it since. I know that it's true that there's actually a 3/2 that comes out here. So that when you calculate A dot over A squared, you get 2 times 4 is 8, divide by 3, 8 pi over 3 G rho. And you can check that. Oh, there's a half here. I'm sorry. There's 1/2. There's always a half here. And somehow these two combine to give you the 3/2. The sign somehow gives you not somehow, does work out in such a way that you don't get 1/2 A dot over A squared, but actually 3/2. Okay, so that's the flat space case. Now, there's another term in the curvature which would be there even if the scale factor wasn't changing with time. If the scale factor wasn't changing with time, but if space was curved, no change, no time dependence, but curved space, then again, space-time has curvature, just by virtue of the fact that space has curvature. So, when space has curvature, there's an additional contribution here. And guess what? That contribution is apart from numerical factor, let's say 4 pi, what did I have there? G times rho. The other factor that's here is 0 when k is equal to 0, but for the other two cases, it's plus k divided by a squared. Now, this is probably not true. This is probably 3/2 of this. It's probably 3/2 of this, where k is either plus, minus 1, or 0. So the meaning of this equation then, let's get rid of the 3/2 by multiplying. It becomes 8 pi over 3. Again, this is the space-time, or this is the Einstein tensor when ordinary space is flat, and it comes from the time dependence of the scale factor, oscillation or whatever it is of the scale factor. This would be there even if the scale factor was not time dependent, just from the curvature of space. Right? It comes in with a positive sign for the sphere and a negative sign for the hyperbolic plane. Positive curvature, it comes with a positive term, negative curvature with a negative term. This is Einstein's equations when you go and plug in that particular geometry into the Einstein field equations. And so what do you get? You get exactly minus 0 for flat space time, or sorry, excuse me, for flat space, and otherwise k over a squared, period. That's it.
Don't you get a factor like r or something like that?
What is r?
The radius of curvature of this.
That's this. That's 1 over a squared here. That's it.
Okay.
Right. Okay, so good. So for simple geometries, curvature is usually just 1 over the radius of curvature squared. That's all curvature is for a sphere or a uniformly curved surface. For a uniformly curved surface, curvature has units, incidentally, of inverse length squared. For a given shape, the curvature will be inverse to the radius of the thing squared. So that's what this is here. And it's either plus 1, minus 1, or 0, depending on which of the cases we're talking about. Okay, so don't think of k as a number that can take on any value. It's either plus 1, minus 1, or 0.
You could have k take any value if you redefined a.
Say it again?
If you redefine a, you can get k to be any value.
Okay, good. Under what circumstances can you redefine a? And to what extent have we defined a? No, you're asking the right question. For the flat space case, there is no unique definition of A. We can rescale A. There's no particular thing to compare it with. All right? But in that case, K is 0, so you can't change it. In the other two cases, there's a natural scale for A. In the spherical case, we can take it to be the radius of the sphere. All right? If we take it to be the radius of the sphere itself, then k is plus 1. In the negatively curved case, there's also a notion of radius of curvature for a negatively curved space. I won't describe it in detail. But again, in that case, it's just minus 1.
What are the other values of T?
What is the other one?
Are all the other values of the energy momentum tensor 0?
No, not in general. Not in general. For example, the space components can be the pressure. Okay, so for the matter-dominated universe, the pressure is 0. For the radiation-dominated universe, the pressure is 1/3 of the energy density. We did that the last time. And remember, we had an equation, just mostly definition, that pressure is equal to W, definition of W, times, what do we call energy density? Rho, I guess. And the three cases of interest, what W equals 0, 0 pressure, that's called matter dominated. W equals 1/3, that's called radiation dominated. Say it again? And -1 for W equals -1 for vacuum energy.
So if you just had matter, all the other components of T would be 0?
Yeah. Right, but the main point is, since there's only one arbitrary function in this setup, again, we've assumed a lot, but once you make all those assumptions, there's one arbitrary function, so you really only need one equation. And you could choose other ones. This one's the most convenient. Yes, K is equal to +1 for the sphere, -1 for the hyperbolic plane, and then 0 for the flat space. Right. Yeah. Okay, so we see that Newton's rules don't really lead us astray. They give us the right answer, but the Einstein equations adds one new ingredient. We can think of this K in two ways. From the Newtonian point of view, it simply has to do with whether we're above or below the escape velocity. Okay. From the Einstein point of view, it has to do with whether we're above or below the escape velocity, but also what the geometry of space is. Okay. Now, I think we can end there for tonight. I think I've reached a good point to stop. What I should spend a little bit of time next time is just discussing the significance of the cosmological constant and how it affects the behavior of the solutions. But again, let me just point out right now, at least before there was a cosmological constant, pre-cosmological constant, there was a tight relationship between whether you were above or below the escape velocity and whether space was positively curved, negatively curved, or zero curved. How so? If space was positively curved, K equals +1, and that meant you were below the escape velocity, the implications being the universe would expand and then recontract. You can see that in the equations. We'll study the equations a little bit further and see that. I'm a little too tired now to go through it. If K is bigger than 1, is +1, sorry, if K is -1, then you're above the escape velocity and the universe just continues to expand. And K equals 0 is the marginal case, the knife edge in between, where it does continue to expand but at an ever decreasing rate. So that's the new thing that general relativity adds into this analysis. It adds many things, but that's the central thing that it does, is it connects the question of above or below the escape velocity to the question of geometry, whether geometry is flat, round like a sphere, or saddle-shaped like the hyperbolic plane. So it provides a correlation, a new kind of correlation. And that brings us to the conclusion for tonight. And I'm going home and going to sleep, and I will not see you next week, unless you're in England.